Okay, so today we're going to have a look at the final thing in our further calculus topic, which is volumes of revolution. So, just for fun, what if we had a function and we rotated around the x-axis? Who thought that would be useful? But, just when we thought the fun would stop, we go on. So, volumes of revolution are all about getting functions and rotating them around either the x-axis or the y-axis, and they form particular shapes. So, for example, if I had this function at the top and I rotated it around the x-axis, I keep going around and around and around, I would get this funny looking vase shape here. If I got this shape and I rotated around the x-axis, I would get this shape here. If I got this one and I rotated it around the y-axis, I would get a donut. We actually call it a torus. Or if I got this straight line and I rotated along the y-axis, we would get a cone. So volumes of revolution are all about getting functions and figuring out what their volume would be if we rotated it and made some sort of 3D shape. Now it has a multitude of uses, so we're not just doing it for fun. One of the more pure mathematics applications of this is finding formulas for volume and also surface area of particular shapes, specifically cones and spheres. But also there are other actual applications. So for example, if we had a CNC or 3D printing machine, it would use particular rotating formulas to figure out how much material, if it was solid, a print may require, all the way down to, say, optimizing the form and volume of rockets or bullets, because they could form that type of circular cylindrical shape. So basically anything that could form a cylinder, curve, or rotated like shape is relevant. So even, for example, we can get computers to estimate curves along particular objects, rotate that curve, and then we can figure out its volume. So rotating about the x-axis. Now, textbooks, they really just superficially show you how to do this, and unfortunately in Extension 2 they took this topic all out of the syllabus, so they've really grossly simplified this whole topic, but we just have to go on using this simplified version of it, but I guess it makes it a bit easier for us. But I would personally like to show you how we actually do these integrals and how we figure out these volumes. And back in the day when I did it in Extension 2, we had to prove this every single time when we did more complicated volumes. But at the moment, we're just proving the formulas and then we can use them from here on out. So let's say we've got this region here, f of x, and we rotate it around the x-axis. We might consider a small cross-section. Now if we cut it vertically, all of our cross-sections are going to be circles, and that is going to be the case with all volumes of revolution. Your cross-sections will always be circles. In fact, in the old Extension 2 course, we utilised that fact to calculate volumes through a method known as slicing, and also another method known as cylindrical shells, which we don't do anymore. Now, if I was looking at a random cross-section at point x, so a cross-section at point x0, it's going to look like this. It's going to be a circle, and its height is going to be the value of the function at that height, f of x. So the radius of this cross-section would be f of x. And let's say it has a random thickness dx. So the thickness of that cross-section is dx, some random thickness. Now the area of that cross-section would just be pi times the radius squared, pi times f of x squared. And the volume would be pi times f of x squared times by the thickness. The volume is just the area of its base times by its height. So pi times f of x squared times dx. But obviously one cross-section is not good enough. And 3 cross-sections, 4, 5, even 100 cross-sections is not good enough to find the exact volume of this shape. So to find the exact volume of the shape, we really need an infinite number of cross-sections. But if we put an infinite number of cross-sections along this shape, then they'd all have to have an infinitely thin thickness. So that means dx has to be infinitely small. So what are we actually doing? We're adding together an infinite number of cross sections that are infinitely small. So as an equation, the volume would be the limit as dx approaches 0, so as our thickness gets smaller, of the sum of all of our cross sections. So the sum of all of those cross sections from A to B, those were the limits. We started at A and we're integrating to B. Now that is our formula, but we've seen this before. This is another way, we have a symbol for that, and it's an integral. So volume is the integral of pi times f of x squared dx from A to B. But we know that f of x, well, if it's equal to y, it's just going to be, or f of x is equal to y. So the formula when we rotate about the x-axis is pi times by the integral from A to B of y squared dx. Now please, we always draw a picture when we do these. So we've got the region between the lines x is 2, the x-axis, and the function y is 16 minus x squared is rotated about the x-axis. So we've got this function here, that's actually a circle of radius 4, from 4 to minus 4. That's going to be 4 up here, and it's rotated about the x-axis. Now, our formula, we've got, first up we're going from the region. Let's look at what this question says. The region between x is 2, the x-axis, and the function. So that's this area here. And we're rotating it about the x-axis. So we're forming this funny looking shape here. It's going to be like a weird bowl. So the formula is volume is equal to pi, the integral from A to B of y squared dx. Volume is equal to pi, we're integrating from 2 to 4. Now y squared is the square root of 16 minus x squared squared, so 16 minus x squared dx, which is equal to pi times by 16x minus x cubed on 3, from 2 to 4. Now if you substitute all of that in, you will get pi on, no you don't, you get 40 pi on 3. So I might actually just make it clear what I'm doing there. I'm substituting in 4, so 16 times 4 minus 4 cubed on 3 minus 16 times 2 minus 2 cubed on 3, which is 40 pi on 3. Okay. Next one, we're determining the volume of the solid formed when this shaded region is rotated about the x-axis. So we're rotating this about the x-axis, and it's going to be some funny looking horn shape that looks like this. Maybe it's like a witch's hat or something. It kind of looks like the sorting hat from Harry Potter. So our formula, we're looking at the volume is equal to pi times the integral from A to B of y squared dx. Now this is an odd function. Now I don't mean odd as it's strange, it literally is an odd function. We can see that x cubed is odd. Now it might make our lives a bit difficult if we've got minuses in this. So we might integrate, instead of from minus 1 to 0, we might integrate from 0 to 1, because it's going to be the same. Now we're looking at y squared. Now x cubed squared is x to the power of 6 dx, which is pi times by x to the power of 7 on 7 from 0 to 1, which is pi times 1 on 7 minus 0, which is pi times 1 on 7, which is pi on 7. Okay, number 3, I've got a champagne flute is designed by rotating about the x-axis. The region between the curve y is 4 plus 4 sine x on 4 about the x-axis from 4 pi to 6 pi. Find correct to 4 sig figs the capacity of the flute. Okay, again, we're going to draw a diagram here. Now we've got sine of x on 4. Normally the domain of sine is from 0 to 2 pi. Oh, that's like the period, pardon me. Now, x on 4 stretches it, so it's going to make it 4 times as large. So times by 4, our new domain, or our new period, is 8 pi. Let's draw that in. So that's, we might do it twice, that's sine like that. So this is now 8 pi, which makes this 4 pi, which makes this 2 pi, and this 6 pi. That's going to be 10 pi, 12 pi, 14 pi, and 16 pi. Now it's a 4 sine x on 4, so this is 4 up here and minus 4 down here. But we're adding 4 to that. So really we're going to get this function and move it up by 4. So that's our function there. And we're integrating from 4 pi to 6 pi. So we're looking at this weird shape here. We're rotating about the x-axis. We're looking at this shape here. So again, we're looking at the volume is equal to, we're integrating from 4 pi to 6 pi, and it's going to be the equation squared, 4 plus 4 sine of x on 4 squared dx. To do that, we need to physically square this, so the integral from 4 pi, we need to put a pi up the front as well, 4 pi to 6 pi of 16 plus, what's that, 32, I think? Yep. Okay. Now these are all very easy to integrate apart from that last thing. We might take out a factor of 16 to make it a bit easier. 16 pi, the integral from 4 pi to 6 pi. 1 plus 2 sine of x on 4 plus sine, that should be a squared down there, sine squared of x on 4 dx. Now we can't really integrate sine squared as easy as the other two, so it's 16 pi, the integral from 4 pi to 6 pi of 1 plus 2 sine of x on 4 plus a half of 1 minus cos of x on 4 times 2, which is x on 2. And now we can probably just integrate this now. We've got, oh actually I reckon we can expand it a bit more. 4 pi to 6 pi. Now 1 plus 1 on 2 is 3 on 2 plus 2 sine of x on 4 minus 1 on 2 cos of x on 2 dx. And now we can integrate this. Did I leave any more room? Yep. Now we can integrate this. So 16 pi 3 on 2x plus, now if we integrate sine of x on 4, we're going 1 over 1 on 4, which is 4, so we've got it 8. 4 times 2 is 8 cos of x on 4, and that needs to be a minus because the integral of sine x is minus cos x minus a half times 2, so minus sine of x on 2 from 4 pi to 6 pi. Now that's a lot to substitute it in. If you substitute all of that in, you'll get 71.62 milliliters. A long one but a fun one again. Thank you.